Yeah, crack on, go for it. Who's best?
Hello, how are you doing? Good, thank you.
Just
No, my best guy friend is coming to visit right now, and he is also being mad at idiot and was like, please.
actually, I thought that.
He doesn't really work in high school, so I had to spend some time with him. But they were I know, honestly, it's not. Honestly, it was it's entertaining. Like, I was entertained.
Last is like
Fairly.
The last time I literally
like that's like our expectation for like YouTube. Like 17, that's not us. I'm not an occasional Yeah.
There's also one I wanted to
Were you like crying? And about something. It's quite, I mean, it's relaxed, but he seems quite frantic. So he thinks that's.
I think he's good.
And never stops. Oh, he's like the stereotype. I was actually working on it. I was like, friends and like
Okay, so welcome back. So this week we're making one of the big shifts that we make in the course. We spent 4 weeks talking about the physical climate system and the impacts of climate change. Starting today, we're going to be thinking about reducing greenhouse gas emissions, okay? What we call mitigation of the climate change context. And this week is very much about taking a macro view of the problem, just understanding the emissions pathway we're on, understanding how we get emissions pathways that are consistent with climate goals, and thinking about how we bridge the gap from the former to the latter. Okay? So I asked you to watch at least a couple of videos before you came today. The first, what drives greenhouse gas emissions, just looking at emissions trends, emissions patterns around the world, and also trying to think about the relationship between economic growth and emissions using the framework of the Kaya identity. Okay, hopefully that sounds familiar to you. And then in the second video, we used that framework of the Kaya identity to think about where we're heading. So what would a baseline emissions pathway look like? And then I explained to you how these Paris-aligned scenarios, these low-carbon scenarios, are derived, right? Thinking about the carbon budget and so on. And eventually, we landed on this concept of an emissions gap, didn't we? Which is literally the difference between the path that we're on and the path that we need to be on. Okay? And what we're going to do in class today is we're going to talk about bridging that gap. And we're going to break that problem up into 2 parts. The first part is just a question of technological feasibility. The question is, can we actually bridge that gap, irrespective of cost? Do we have enough technologies and ways of doing it? Okay? And what would what kind of technologies would we expect to use to bridge the gap? So the first part of it, Mini Lecture 5.3, is really going to be about technological feasibility. Of course, technological feasibility doesn't really tell you about which options you should take. For that, we need to think about the economics of the various options, and we'll also think a little bit about political feasibility. So that is what we're doing in Mini Lecture 5.4. And the assignment is sort of supports Mini Lecture 5.4. I'm actually going to do it in between the two. And it gets you to think about a global marginal abatement cost curve, which is a wonderful way of obtaining some stylized facts about the transition. Okay? And then lastly, we may or may not have done this already. Because I don't really have time to do it in class, I've recorded a short video on so-called geoengineering, which is a set of ways of dealing with the climate problem that don't involve reducing greenhouse gas emissions at source. Okay? And they include various methods of carbon dioxide removal from the air, some of which, that's a bit of a blurry boundary between what we'll be talking about in class, kind of conventional mitigation technologies and geoengineering. And then the other thing I talk about in this video is the more exotic solar radiation management, which is literally trying to change the energy balance by preventing some incoming solar radiation. Okay, so you can watch that at your leisure. Okay, so with that, then the first thing is going to be to do Mini Lecture 5.3. So let me go to that now. The sign-up sheet, by the way, should be passing around. Do make sure you sign in so you can avoid a bit of correspondence in case you were here and didn't sign. Okay, so here we go. So So I want to say to begin with that this is not rocket science. So if you're sitting in this mini lecture and you're thinking this all seems a bit too easy, what am I missing? You're actually not missing anything. Okay, this should be easy. Well, I hope it'll all be easy, but this is particularly easy. Okay, so all we're trying to do here is understand what the different technologies are that we might use to bridge the emissions gap, which I'll explain to you in mini lecture 5.2. And the organizing framework I'm going to use for this is an idea that was made popular in the mid-2000s. It's the concept of a so-called stabilization wedge. It was developed by a group of scientists at Princeton, led by Rob Sokolow, and it still exists there under the auspices of a project whose name I've temporarily forgotten, but will remind myself of. The Carbon Mitigation Initiative. So you can go online if you want and find out a bit more. I'm actually going to use some of their materials here to get us started. But okay, so what is a stabilization wedge? Well, basic idea is simple. We take the emissions gap, right, which is this area here, and we're going to divide it into a set of equally sized wedges, and then we're going to think about whether there are enough commercially demonstrated technologies out there to make up the wedges that we need. Okay? As a way of just demonstrating that bridging the emissions gap is actually feasible. Okay? Not rocket science, as I said. Basic point being is if we could not think of, if we did not know of enough technologies to make up all these wedges, then we could not say that it was even feasible, let alone economical, to bridge the emissions gap. Now, so hopefully that idea is quite simple. What does stabilization mean in this context? They offer two interpretations of that. Firstly, emissions stabilization, and secondly, climate stabilization. So it's not super important for this mini lecture, but just to see how much you've been following the course up to this point, let me ask you a question. What in this chart looks a bit outdated?
The year from the current one is 2000.
Oh, sure. Yeah, no. Is it not the year 2000? Sounds like my mother. Yes. So clearly we've moved along here. So we are further along. Emissions have gone up, and but technologies have also developed. Okay. So our starting point has shifted. Agreed. Yes.
It's measured in carbon, and I think nowadays we mostly use CO2 or CO2 equivalent.
Yeah, I mean you can use either, but it is a good point. What is the exchange rate between carbon and carbon dioxide?
7.6.
That seems a bit high.
No, 2.7.
That's a bit low.
367.
Yes, 44 over 12, right? Because that's the atomic weight of CO2 relative to C. Yeah. So just I mean that's not crucial. So if you want to convert this from carbon into carbon dioxide, you have to multiply by 3.67. Yes.
It was maybe a bit outdated is that does not include net zero.
Yes, exactly. I think that's one of the main points I want to get across here. So climate stabilization here. I mean, this idea is, I mean, okay, this is quite stylized as well, but this framework predates the idea of net zero by 2050 as being a feature of emissions pathways that limit warming to 1.5 degrees with no or limited overshoot. Okay, so I wanted you to particularly notice that. Emission stabilization, what would be the problem with that?
I mean, it's still a flow, so if the flow is stable, but the we still have increasing stock, therefore we still have warming temperatures.
So emissions will, if we only stabilize emissions, temperatures will keep going up. And I explained in mini lecture 5.2 that, roughly speaking, temperature is a linear function of cumulative emissions. Okay? So if we only stabilize the level of emissions and we don't reduce it to zero, temperatures are just going to keep going. So, okay, good. So you've been following. Yes? Sorry.
Maybe a question on that. You hear it every time again, but are we now finally stabilizing? Are we peaking in terms of CO2, or I believe this, I hear this every 6 months or 12 months ago.
So, okay, let us pause, go to our world of data, greenhouse gas emissions. Global GHG emissions. No, I don't want them by sector. Hopefully we're going to get the latest data in this chart. Yeah, so you see this? So, are we peaking? Well, we're bending the curve, right? So we're flattening things out, but we could not say that we've yet peaked. I would have been a bit more optimistic about that a couple of years ago, but things are keeping going up. Okay, but back to where we were. So yes, you got it. So I just wanted to make sure you had followed up till now, but basically, to stop temperatures from increasing, we have to get emissions to zero. The earlier we do that, the lower the temperature at which we stop. Right? If we just stabilize emissions, temperatures keep going up. But other than that, this stylized framework is going to be helpful. So we're going to be focusing on identifying enough technologies which make up a wedge, which is just arbitrarily defined as a strategy that reduces emissions from by 1 gigaton of carbon per year in 50 years' time. Building up gradually, right? So it's the area of a triangle. This is going to be a total of 25 gigatons. As I'm sure you can see, these numbers are arbitrary. Okay? It's just intended to break up the problem of the emissions gap into a set of equally sized chunks. Yeah? And as I said, the aim here is to identify a set of technologies, each of which makes up a wedge. Okay, so in the original framework, there were 15 wedges, and they divided them into 4 categories: energy efficiency and conservation. Go around clockwise. Fossil fuel-based strategies, which already might sound like an interesting concept, because you might be thinking, well, I thought the whole point was to get rid of fossil fuels. Renewables and biostorage, as they called it, and nuclear power, okay, which sits out on its own because it's low carbon but not generally referred to as renewable. Okay. Digging a bit deeper into these 4 areas, and some you can see the age of these slides. This is deliberate. I'm not being lazy here. So 3 different wedges in the energy efficiency and conservation category. So the first one is just to improve power plant efficiency. So this is a specific manifestation of a more general strategy, which is to increase energy efficiency. Okay, so to be able to supply more energy with less fuel input, or more useful services with the same amount of energy. And that's going to come up again and again today. Increasing the fuel efficiency of cars. Okay, so hybrid vehicles were the future when these slides were put together. And so that constitutes it. Hybrid vehicles are just more efficient vehicles with internal combustion engines, is a wedge. And then energy efficiency in residential and commercial buildings. So it's the category of energy efficiency measures, broadly speaking. Fossil fuel-based strategies. Okay, so this is an interesting one. So you could make up a wedge by by switching from coal power plants to gas power plants. And that's because gas is much less carbon intensive fuel per unit of energy supplied, as I'm sure you know. This leads to a very interesting debate about the extent to which we could think of gas as being a transition fuel, which is a debate that surfaces in a lot of different contexts. But just from a technological point of view, this would, if the baseline here were electricity produced by coal, then yes, you could definitely reduce emissions by eventually 1 gigaton of carbon per year by just switching to gas. And if you think about places that have done coal to gas switching, like the US, you can see that it was effective in reducing emissions, even if climate policy might not have been the primary driver. In the US, it was the shale gas boom. Okay, so that's a fossil fuel-based strategy. Another fossil fuel-based strategy is so-called carbon capture and storage. Have you all heard of CCS? So some of you have, some of you haven't. So it is feasible to capture the CO2 generated by combusting fossil fuels in an industrial source like a power plant or a steel plant. You can capture it, you can liquefy it, you can inject it in the ground in geological features where it won't escape again. Okay? And therefore you have in principle achieved fossil fuel combustion without carbon emissions. Okay? So you can keep using fossil fuels without emitting any CO2. And for now, we're just going to think about this in relation to concentrated industrial point sources. Principally, we're thinking about power plants here, but we could also be thinking about things like steel plants or cement plants, places where fossil fuels are burned in large quantities. Yes.
It may not be efficient, but can like reforestation be considered as a carbon capture strategy?
We'll get there. Yeah. I'm not. Here we are in the fossil fuel-based strategies category. Therefore, trees don't belong here, but we're going to get there in a minute. So you're right. Yes, growing trees is essentially a form of carbon capture. Yes.
I was wondering how cost-effective is carbon capture and storage compared to the other ways?
We'll get there too.
Okay.
So, at the moment, I don't want to talk about economics for once. I probably won't be able to help myself. But all I want to talk about at the moment is the technologies. Yes.
Does it acidify the water, and how that kind of affects?
I'm sorry.
Does it acidify the water?
Yeah, if it were injected in an aquifer, yes, it would. But this is pretty deep underground, so I'm not an expert in this technology, but I've not heard of that being an environmental concern.
Thank you.
Fun fact is that actually, the technology to do this is a technology that oil and gas companies in general are pretty good at. Right? They're good at getting stuff out from deep under the ground. They're also pretty good at injecting things deep under the ground to help get fossil fuels out of the ground. Therefore, oil and gas companies would have a competitive advantage in doing this kind of work. And one of the largest oil and gas companies in the world, Occidental, or Oxy, has a long-term strategy which sees it proposing to do this a lot. Fun fact. We'll come back to that in week 9. Yes.
Just what you know about cost and the feasibility of introduction of carbon capture and storage into the mainstream industries.
As I said, I don't want to talk about costs. at the moment. I want to do that later. But in terms of feasibility, this technology has been demonstrated. Okay? There are of the order of a couple of dozen demonstration facilities around the world that do this. Maybe my technology, I might be 1 or 2 years out of date with that number, but it hasn't taken off yet, and that could be a question of the economics, but it works. You do need to, you can't just stick it anywhere, okay? So typically abandoned oil and gas wells are where you would put it back. So there can be an issue of getting it from where it's emitted to where you want to store it. But now I'm getting into the economics. Okay, one more question about that.
So it would like, probably we needed to also relocate plants if the surrounding natural area does not provide like the
Yeah, or pipe it.
storage or pipe it.
Do either. Okay, so that is, so then we're on to the third set of wedges, which is just a set of one. It's a singleton set. It's nuclear. Okay, so nuclear is zero carbon, essentially, at least from the point of view of the power plants themselves. And so, you know, a large build-out of nuclear plants of the same kind of order as we saw during the kind of golden age of nuclear power from the mid-70s to 1990, that would also give us a wedge. Okay. Then we're on to renewables and biostorage, so now things that you will all be aware of, so wind. Don't need to say really anything more about wind, except that these numbers are quite out of date in terms of the capacity of turbines. The turbines have got bigger, a lot bigger since this work was done. An offshore wind turbine could have a capacity of something like up to 15 megawatts now, compared with, say, they were thinking along the lines of 2 megawatts. That would be a bit more what you would expect for an onshore wind turbine, where people don't really want us to live next to really enormous turbines. Okay? But wind, so wind is a wedge, no question. Solar as well, that also needs no explanation, except to say that the kind of solar you see here in the pictures, solar photovoltaics, that has become the dominant solar technology, but there is also in principle concentrated solar power. Have any of you ever heard of that? So you might have seen these plants in the desert where they have essentially like a big mirror and a set of panels arrayed around the mirror, and the mirror just sort of increases the amount of solar radiation going to the panels. Okay, so it's an attempt to make it to increase the capacity. And the other thing I want to say is that I just want to allude to the fact that Stephen might have talked to you about this in his course, actually, this debate about whether we should have sort of grid scale solar, whether we should build these solar farms, right, where we just lay out dozens or hundreds of panels in like agricultural fields or on tops of car parks and things like that, versus just sort of micro scale solar. And that's a really interesting discussion which plays out in the context of energy policy. So in Stephen Jarvis's energy policy course, I guess you might touch on that. I don't really have time to get into it. Biofuels, okay, so biofuels you can kind of divide into first and second generation. So the old way of doing biofuels was to do things like make ethanol out of corn or sugar beet. Or make biodiesel out of soy. So these are food crops that you can turn into fuels. Okay? And you know, I mean, I don't know if any of you have ever seen one of these car shows where they try to just put vegetable oil in a car and try and run it. I mean, it basically pretty much works, right? But with a bit more sophistication, you have a good substitute. Okay, modern biofuels, second generation biofuels, that's more things like dedicated energy crops, things like machanthus, right? These kind of energy-rich grasses, and also waste wood and waste organic material. Okay, they could be biofuels. Who has heard of a very ominous-sounding Drax? Right? You heard of Drax? Again, if you did Stephen's course, I guess you've probably heard of Drax. Maybe. I think he had one of his companies in that game. Was
Yeah, there were two of them.
Yeah. Okay, so Drax is a big power plant in Yorkshire, in the north of England, which used to burn coal, but now burns wood pellets. So it is, strictly speaking, burning second-generation biofuel. The question is a little bit, where does the wood come from? Is it really waste wood or plantation wood, or is it actually wood from virgin forest? There's been a lot of attention to Drax's supply chain. Okay? But just focusing on the technological thing, Drax is an embodiment of biofuel as a stabilization wedge. Next category they call natural sinks, and they put various things together here. So this basically ways to use nature to either avoid carbon emissions or to take carbon out of the atmosphere. So eliminate tropical deforestation. So if your baseline is that a forest is going to be cut down, then avoiding that reduces emissions. This is going to be really important in 2 weeks' time when we talk about carbon markets, because in carbon markets, a lot of credits have been traded on the basis that deforestation will be avoided. But the question is, were the people selling the credits really planning to cut down the forest, or were they all not planning to do it anyway, so that it was just another way of making money for them? Okay? But in principle, if your baseline is that the forest is going to be cut down, then eliminating it is going to reduce emissions. Reforestation and afforestation, so this is growing trees, and of course trees absorb CO2, so that's going to take CO2 out of the atmosphere, and that is a form of carbon dioxide removal. And then the third in this category is something called conservation tillage. Basically, when you till or plough soils, it releases CO2, right? And so I think it's CO2. Correct me if I'm wrong. I'm pretty sure it's not N2O. And so if you can adopt agricultural practices that would lead you to till the land less, then you will emit less carbon or N2O. Yes, you've been itching to ask the question.
Yeah, the biofuel, doesn't it still emit CO2 because when you burn?
Yes, so the idea is that there's a balance between the CO2 absorbed during the growth phase of the plants and the CO2 emitted when burning. That's actually an important point, right? So it's an important question from your colleague at the front. So if you're burning the biofuel, how come that reduces emissions? The answer is when you grow the fuel in the first place, you take emissions out of the atmosphere, right? Unlike fossil fuels, which did their growing hundreds of millions of years ago. Yeah.
I was also thinking about the materials we need for wind or solar, as lithium or rare materials. How also mining are also a contributor to emissions globally and how they consume a lot of power. Has this trade-off has been measured before? About how much emissions?
Yeah. So the sorts of, first of all, you're right to think about, absolutely right to think about supply chains. With these kinds of frameworks, simplify by trying to think about specific emissions avoiding technologies, basically at the point of emission. The point of emission itself can be at different places in a supply chain. It could be upstream or downstream, right? You want to think about the wider supply chain, and things like how much is emitted in extracting and refining lithium for batteries, or how much is emitted in extracting and refining uranium for nuclear plants. That is not explicitly dealt with here, but the kinds of integrated model that we'll talk about later today, they do capture the whole economy. So if that were a major problem, it would show up in the models. Yes, I just wanted to find out where I was.
With conservation tillage, does that mean like crop rotation, or is that more?
Yeah, stuff like that.
Okay.
Yeah, or leaving the crop, figuring out ways to leave the crop residues.
Okay, so like just maintaining the soil.
Yeah, rather than the standard ploughing after. I mean, I'm not a farmer, you could tell, right? But I mean, that's the basic idea. Yes. So, hopefully that was straightforward, and it's helped to brainstorm some of the ways that we can reduce emissions. Now, I basically started here with this work and used these old slides because I thought it would be interesting to get you to think about how that picture compares with our sort of contemporary understanding of how to reduce emissions. So I've got a sort of discussion task for you now. I want you to think about how we can update the list of stabilization wedges that I've just described to you. Now, simplest way you can approach this task is just to ask yourselves, what mitigation technologies am I aware of that he has not mentioned yet? You may also extend that to thinking about which of the technologies has he mentioned that I don't think, that I think we now know don't work or aren't relevant anymore. Those are the two questions to ask yourselves. So I'd like you to spend 10 minutes with your colleagues around about you, see if you can think of any mitigation technologies that I haven't yet mentioned, or if you have any comments about the technologies I have mentioned, maybe not being relevant anymore. So 10 minutes from now, off you go.
With you? Yeah, no. The rest of the day, I guess. I'll say that I just know that yes, I think that's I would try to understand.
What? Wait, no, I'm really like I was like this on the bed, I was literally like, so
I might actually say
yeah, natural-based solutions. So bad on Saturday.
yeah.
Like 3 to 6 weeks will be fine.
So I guess there's still that.
I don't know.
So,
Driving on something probably
and then I have this random friend from Holland, like town. She was like at this next to us.
Yeah, of course.
But then it took us like 30 minutes to get there, so then we finally got to the and there was cover, and I was like, I saw it touch of
I'm just putting the book. I'm trying to
Yeah.
I've always had that in mind, and I did it for a long time, and at the end I was. Then you do more and more management.
could be saying
Very well, and everything right. For me, it was. Yeah, and also very low. Just a lot of process. And also a lot of, you have to present, you have to do the boss, you have to. I wanted to do a second career, and it was really like the last limit. Not the limit was then you stop. Yeah. Also, your time it takes and you 60 and then exactly. And you I guess like about the games. But anyway, it's very, very great to do something completely Not yet. Yeah, we'll see. I'm trying. I haven't done it. I've done it yet, but yeah. Yeah, exactly.
Yeah. 2 minutes.
Yeah. But it's very, it's very hard when you have a family and everything, and I think it was a big job. I tell you, for many years I told my wife I'm gonna do a job, and then she was like, yeah, whatever. And then one morning I say, okay, it's today. I'm gonna go to the office and I'm gonna do after one is university, that's 18, and the other one is 15, 16. He's doing GCSEs here. It's a big change for them as well, but it's quite funny because my son is he's got
Okay, let's hear about some of the things you came up with. So, what about down in this corner of the room? Have you come up with any additional wedges? Yeah, that's a good one. So hydrogen. It would need to be green hydrogen, right? Because current people, hydrogen is produced at the moment, but using natural gas, generally speaking. So they would need to make it out of water using electrolysis. Yes. Oh, great. Yes, exactly. So it's not a direct sort of mitigation technology, but it is necessary to support things like wind and solar and so on, isn't it? So electricity transmission and distribution, absolutely, and that'll come up later as well. Yeah, very good. Okay, over into the far side, even further side. I'm looking at you guys. Yes.
We talked about the solar radiation management. That was the mini lecture 5.5 as those being options as well.
Yeah. So I'm gonna that is an option for stopping temperatures increasing, but I'm putting it out of the scope of what I'm talking about just now, which is sort of technologies which avoid CO2 emissions or reduce the CO2 concentration. And solar radiation management doesn't do that. Yeah.
This might also not. So, like smart technologies, like smart meters.
Yeah. No, that's absolutely valid, and we will talk about that more in week 8. Okay, because it doesn't directly reduce emissions, but these are technologies which might produce a behavioral response, which causes us to reduce emissions. Yeah. Okay. I'll yes, at the back.
Sustainable aviation fuel.
Yes. So sustainable fuels, particularly for aviation. Aviation fuels, absolutely. Yeah, nobody's yet managed to build a sort of a commercial battery-powered airliner. I certainly wouldn't want to get into one. Okay, so sustainable aviation fuels that are combusted seems like currently the best bet for that. Yes?
Hydropower?
Hydro, yes, that's right. A long-standing technology, but a very valid one for reducing emissions. Yes?
We'll just debate about like a range of transport options were kind of felt like missing from the list, or does this fit under kind of halving miles travel? Like that we even back then have train active travel that we could be encouraging more people to do.
Modal shifting, they call it in transport. Absolutely. So line bikes and things like that, right? Or just taking public transport. Yes. Oh, yes. That has that is definitely relevant, but has an ambiguous effect, I guess, because on the one hand we have all the data centers and the energy consumption, on the other hand we have technology which could make us more energy efficient. Yeah.
So about nuclear fusion. Nuclear fusion.
Fusion? Yes, yes, because we only spoke about fission so far, didn't we? So nuclear fusion, which is always nearly with us. But I did read recently that it might be more nearly with us than before. Yeah.
Batteries?
Yes. Battery storage, again, doesn't reduce emissions by itself, but in common with things like transmission and distribution and smart technologies, it can facilitate emission reductions.
Marine conservation protected areas, so that forest.
Oh right, okay, yes, right. As a form of carbon dioxide removal, right? Yeah. So sort of marine CDR, I'll call it. That's not a technical term, but you can grow plants in the oceans. You can also do things like put iron filings in the oceans that help capture carbon.
We also spoke about sort of the scale between the different wedges, and we sort of thought that like those all the carbon sources really had like the world in a chokehold, and you could barely go without like this. And solar and so on has scaled up much more than we would have expected. So it's actually much bigger scale than we would have thought 20 years ago.
Oh, yeah, yeah. So some of these might be more than just a single wedge. Yes.
You talk about tidal energy?
Tidal, yes. Yeah. Yeah, so you can put some turbines under the water where there are regular tides. That's right. Way at the back.
Geothermal?
Yeah. Which is where Iceland gets most of its energy. Of course, you've got to be somewhere that is volcanically active for that to be particularly viable. Yes.
Afforestation?
Pardon?
Afforestation.
Afforestation, yeah, we sort of had that in we did have that. So plant new forests. So you're right. We've already got it on the list. Yeah. Yeah.
Maybe specifically like non-market-based behavioral responses.
Okay. Yeah.
For energy conservation, maybe.
Yeah. Absolutely. So that is not a technology as such, but it's important to shift the reference a bit towards thinking about the demand side or the behavior side. Yes.
Carbon farming. Carbon farming.
Carbon farm.
Farming. So like land management techniques.
Yeah. So okay. So yeah. So I'm just going to call it low carbon agriculture. I mean, conservation tillage we've already talked about. That's one, but there are other techniques in that category. Don't ask me to list them all. Yeah.
Sorry, maybe it's just like a no-brainer, but we haven't mentioned electric cars yet.
We have not. Thank you. EVs. Why have we not mentioned that yet? Probably because I showed you some old clunkers running on a hybrid engine. Yeah.
Yeah. Green materials like green cement or something that absorbs carbon.
Yeah. Yeah. That's an option for cement. So. I'm going to call it zero carbon cement. There are a couple of dimensions to that. I'll come back to it in a minute. Okay, there's both the production phase of cement we need to think about, but there's also whether cement could absorb CO2 when it's actually after production. Yes.
Recycling?
Yes. Yes. Normally, you'll use less energy to produce a material through recycling than you will to produce it from the raw material, right? Ordinarily. Yes. Yes.
Small modular modular.
Yeah. So nuclear, which can be sort of large scale, or nowadays there's the small modular reactors. I'll call them SMRs, not to be confused with ASMRs. Yes.
When it's recycling, the kind of
called circular economy.
Yeah, circular, that is important. And it's not a technology, but it's like an approach. We'll sort of pull this together in a minute. Okay, what's the hands for that? Yes.
Direct air carbon capture.
Yes. So direct air capture. So instead of capturing carbon at the end of the smokestack, you can actually build devices that will suck CO2 out of the air, just out of thin air, basically. Yeah.
Tidal energy.
Tidal. Yeah, we've got that here. Yeah. I know the list is so big by now that I'm losing track as well. Yeah.
Electrification of industrial processes and
Yes,
heating.
good. So we haven't we haven't really talked about heavy industry yet. Okay. But so electrification of industry. Mention that a bit more in a minute. Okay, we'll take maybe two more, and then I'll try and pull this together a bit.
Not sure if it's a wedge, but the emission trade systems.
Sorry, I just didn't hear.
The ETS emission trade systems.
Ah, okay. Now I'm going to think about that as a policy instrument, and I'm going to talk about that in 2 weeks. So hold that for me. One more. So yeah.
Yeah, on the demand side, the building efficiency.
Yeah, that's right. I mean, we did. To be fair, we did have that actually. So this is something we've known about for a long time. It's definitely important.
Would you throw heat pumps in that list?
No, I would put that in. I would put that on my list. Whoever said that, yes, heat pumps definitely. And that they did not really exist at the time of the stabilisation wages, but now we think that's very important for buildings where in parts of the world where we need space heating. Okay, I'm going to stop with that, and you'll probably be pleased to know that I have a slide which tries to pull all this stuff together and adds a few things which you might not have mentioned. And I just want to say also that there is no single typology of these things which is just correct. There are lots of different ways that lots of different typologies you could come up with for this, but this is how I've chosen to divide these things. So firstly, I think there are a number of strategies which are about electrifying end uses of energy, like EVs, heat pumps, and electrification of industrial processes. So, a lot of fossil fuel is combusted in industry where they need to generate heat for industrial processes. That can in principle be electrified. Clean fuels for hard to electrify sectors. So hydrogen, you mentioned. Sustainable aviation fuels, you also mentioned. So these are, in some sectors you need very high energy density, basically, and it's not clear whether electricity will be able to provide that. So hydrogen and sustainable fuels provide an alternative. Cutting non-CO2 greenhouse gases, so methane abatement. Methane, three main sources of methane in the world, really. So methane leaks out of oil and gas infrastructure and to some extent coal mines as well. A lot of methane is released from landfills, the decomposition of organic matter in landfills. So don't dump organic waste in landfills, compost it or whatever. And agriculture, both ruminants, right? So cows, sheep, and also rice paddies produce a lot of methane. Refrigerants, okay, so F-gases is an important non-CO2 gas, not as important as methane, but not trivial. So ways of destroying those, okay. Industry, we talked about that a bit, so low carbon steel, low carbon cement. These two ways of doing low carbon cement are production phase, okay, so basically two big sources of emissions in cement production, so sort of directly from the reaction by which you go from limestone to cement, and then also you just burn loads of fossil fuels to get it hot enough in the kiln to actually do that. So two options are reduce the amount of clinker, right, which is where the CO2 emissions come from in the chemical process, and try to capture the CCS, the carbon that's emitted using carbon capture and storage. And chemical sector is a big emitter of greenhouse gases as well. For example, fertilizer production, and also some of the other upstream chemical production processes. Other ways of removing carbon, so bioenergy with carbon capture and storage. So that's basically second generation biofuels and capture the carbon. So then you get the carbon being taken out to the atmosphere and it doesn't go back. Direct air capture, we mentioned that, and things like enhanced weathering, that's basically trying to get CO2 to react with rock, basically. And last, but by no means least, since this conversation usually tends to focus on what I would think of as the supply side, it's important not to overlook the demand side. So we can reduce emissions a lot by reducing the amount of beef and lamb that we eat. It's extremely effective to do that. You don't need to become a full-on vegan. I'm not a vegan or a vegetarian, but I do try to eat as little beef as possible, and that actually makes a big dent in your carbon footprint. We talked about modal shifting in transport, so flying less or switching from cars to public transport or cycling. And we also spoke about material efficiency and circular economy, and basically tied up with the idea of reuse and recycling and longevity. So even when it comes to longevity, this even has some intersection with discussions about how to stop manufacturers making goods that have built-in obsolescence just so they can sell you another one in a few years' time. So, lots of additional stuff here. Basically, I'll just quickly wrap up this lecture and then give you your break. Okay, so first thing I want you to take out of all of this, take out of this mini lecture, is that there are more than enough wedges. I'm not saying that all of these would, I've not done the math, I'm not saying all of these would be a full wedge, but certainly we've got more than enough technologies to bridge the emissions gap. So bridging the emissions gap is technologically feasible. That's the first point. The second point that sort of follows reasonably quickly from that, and I've used a piece of analysis in the IPCC 6th assessment report to prove the point, but it's a pretty obvious point, is that there is no single portfolio of technologies which is necessary to bridge the emissions gap. We can develop multiple different portfolios or pathways involving different proportions of action on the demand side and action on the supply side, different amounts of reliance on carbon capture and so on, that will get us to the same place with the same amount of cumulative emissions and the same temperature. Okay? So that's the second important point from this mini lecture. The first is that it's feasible. The second is that the feasibility analysis does not give us a single unambiguous answer into what do we need to use. Right? It's up to us. Right? There is no single technology pathway or portfolio of technologies which is consistent with the Paris goals. There are multiple. So after the break, we need to start thinking about, well, okay, if that's the case, then what is the best portfolio of all of these feasible portfolios? Okay, so let's take a break, 10 minutes, and restart at 3:15.
Very interesting to see what's going on.
I watched the video just before coming here.
I'm neck right now, but I know I'm like this. I like want to sit like this, but I'm like this kid, not like that. Like I got like yeah. I just want to know. I don't know how I did it. That it was like back to back. I missed it, and then you can't like oh.
message to you. It's like, oh, I don't have my supervisor. I feel like this is going to be
My water bottle. I was like, I need like 3 seconds. I know exactly.
And also how you want
Did everybody sign this?
a lot of
I didn't think so because I saw.
description of the course. He's done lots about
Obviously,
so he's looking a lot about so the course wasn't today wasn't going to be about it's been a good surprise.
I know. I just feel my neck like this.
Yeah, no, I mean, yes, I think that's okay. I mean, I think some materials and compounds can be associated both with the problem and the solution. I think that seems fine.
Activities.
I think this is kind of a headache. Yeah, people try to come up with taxonomies, things like that. And that's when I think about talking about gases.
Just my academic.
A headache.
Yeah. I mean, it's exactly what you want to do that.
I would love to. Like,
You guys manage.
Oh.
Yeah, well, we'll take a look at what the public reckon. I'm aware that is a big debate.
It's like crack jokes like
Well, right. So I think like some of them.
And then I took like my dissertation.
maybe here I'll still be like just like the Simon's out there.
No,
He's doing the work. That's supposed to
You might want to yeah. I usually Sunday and he works as
You mean
Yeah, the one that you did.
yeah, well, I didn't, you see, I didn't, because I didn't want to give the answers away beforehand.
Okay, yeah, but
But you'll be able to watch the recording, and then it'll be on the recording, yeah?
That's what
No problem.
I don't want to go to another ask them.
Has anybody else signed?
It's not like
the job in the case.
I didn't think like you have keep it alive at work.
Last job that you would have those moments.
I am gonna be like, guys,
Yeah, like
you're representing your university. Not
Friends, whatever.
It's very interesting because
Maybe there's more individuals coming. It's really like but it's usually groups.
So I need to see how I'm gonna. That's why it's sort of timing. Will I go there first? No try today. But now the sun's coming out light. Let him at home. Yesterday was but the day before. Yeah, Sunday was running the whole day. Yeah. Now it's this Sunday. Hopefully the sun slowly better.
Second weekend I'm going.
You're going to be around?
Sadly, I'm gonna stay here. I wanted to go to.
I didn't do that last time.
I'm joking. But I can't go by myself, and like I don't have a good passport. Like I can't go to most European countries. So like I only have something like you know the European. I need a visa, and the visa takes. I was talking about this last week. It takes 2 weeks and
April and May.
It's like e-visa, you go, or even Thailand, but nobody wants to do that. At least my friends for like in the States. I might do like, I don't know, something like
Smoothly transitioning from Dubai
to Scotland. Close enough, you know,
You know, I've been as well, but I've been in August. Scotland in February.
I mean, you know what you're setting up for.
Yeah, I don't know, I'll just see. But like, again, not as traveling. So I think somebody
now that it's getting sunny. My friends, so many people wondering. Look at that, you never know.
try to go track it through right now.
It's gonna be doing an hour out of 3.
Even then, it's like the mental.
You apply in the end or? But for AFC, like, I was the one you showed me yesterday, the deadline was today, no? Like, no, it's not bad, good.
Yeah.
Which one? IFC as well, or?
That's gonna end up being a good.
Okay, never mind. Maybe in the summer. In the summer. Maybe that's actually. Maybe we'll just wait till the summer. Then we can get real crusty.
Yeah, for me, I can't apply.
Yeah. This ideal premium. Ideally, I kind of like cycle between that model. That's together. Sometimes I'll just do a bit more of what. But with this one, it's maps module. It's how to get that. It's exactly what you said. It takes me, a good few hours to be like, oh wait, okay, I find
2 minutes.
But this happens every week. Yeah, so I need to revise that. To like half
I guess question tonight is like it's better to applied here. The deadline was mid-February, and then tomorrow I'm gonna go and see another profile. Yeah, right. And in the UK.
Yeah, if you like it, there's a lot of it.
She's very complicated. You send emails, lots of people don't respond. They don't respond. No, you know what? Here. Tomorrow I'm going.
I'm actually worried about it.
Yeah, I found someone who's happy to meet sometime there and see if they can be interesting. And then there is another, I want to get your but the guy doesn't respond. And I was going to find some other people
Around New York.
I think they select the condition of offer, but you need to get some grades.
Yeah, I hope.
Actually, you have to get the grades as possible.
It worked out really well.
Mid-May.
It'll take us a while to get all sorted out.
Yeah, but the situation is mid-August, and I think it's at least a month. Yeah. Yeah, so it starts in September. One PhD program.
I have like a 7% chance. What do you
So we're going to do the assignment, but it's actually embedded in the lecture slides. So I'm just going to start with the mini lecture 5.4. I just reiterate, if you haven't signed the sign-up sheet yet, just come and see me at the next break, okay? Okay, so the purpose of the assignment and the lecture more broadly, firstly to understand the concept of a marginal abatement cost curve. This is a very important concept in climate economics, and you can learn a lot from looking at one. To learn to interpret the evidence from marginal abatement cost curves, and then those marginal abatement cost curves are implicitly or explicitly a component of the models which are used to simulate the low carbon transition and help us understand what an economical low carbon transition looks like, right? So a low carbon transition which is least cost. So that's what we're going to talk about after the assignment. So just quick recap. Where are we? End of mini lecture 5.2, we landed on the emissions gap, right? As quantified most recently by Climate Action Tracker in November 2025. Okay. This is with various estimates of where we might be going with current policies and pledges. 1.5 degrees pathway, corridor, and a large gap in between. Then, before the break, we had a think about whether it was feasible to bridge this gap using the organizing framework of stabilization wedges, and the idea was absolutely. Right? There are loads of technologies out there that we could use to do this. We sort of broadened the concept of technologies to think about demand side shifting as well, things like diets, transport choices, and so on. But we haven't yet brought any economics to bear on this problem and actually think about which of the technologies we would prioritize. And to do that, we're going to use the medium of a marginal abatement cost curve. So this is the one we're going to look at primarily. It was produced by McKinsey in 2013. It's actually not been, at the global level, it's not been updated since then. It would look different now. That's not particularly important for this exercise. Why do I choose the McKinsey one? I choose the McKinsey one because it is the most beautiful. Quite simple. From the point of view of teaching, it is by far the best. Do I think the numbers are the best? Not necessarily. But again, that is not terribly important. Okay, so I asked you to take a look at the assignment beforehand, and what I want to do firstly is I just want to make sure that we all understand what we're looking at. Okay? So I'm going to take you through a series of questions, starting, as my local pub quiz master would say, with the ridiculously easy, and then moving very quickly to the fiendishly difficult. Okay? That's the White Bear in Kennington, in case anyone's interested. Wednesday nights. Where you can find me. Usually winning. I'm going to stop there. Okay, so first simple question. What does the width of one of these rectangles represent?
Is it like a range of how much carbon it could decrease it by, abate?
Yeah, it's not. I wouldn't think of it as a range as much as this is the quantity of emissions, the physical quantity of emissions that could be reduced or avoided by a particular technology. And then the height of the rectangle is cost. Okay. And it's like a unit cost, that's important, right? So here it's euros per ton of carbon dioxide equivalent. So each of these rectangles gives you, in a sense, a unit or average cost of implementing a particular technology, and the width of the rectangle gives you how many emissions you could avoid at that unit or average cost. Okay? You're with me so far? We've got questions already.
Yeah, this might be like just a lack of knowledge, but if I remember correctly, you have like 55-ish gigatons of CO2 equivalent.
Yeah.
And then we get to 38, so the wedge is like would that mean that we can't abate everything?
Let's come back to that. But this is for 2030. So the emissions gap in 2030 is not, I think, as much as 55. We can read it off Climate Action Tracker. So that is going to be from 55 to 25, so it's about 35. And then slightly miraculously, that is about the limit of abatement potential in the McKinsey curve. But that is coincidence, right? Because this was 2013 Climate Action Trackers. 2025. Okay, so we know what the rectangles represent. Next question is, so this is a marginal cost curve. How do I get from marginal costs to total costs? Correct. It's the area under the curve, so to speak. Or if you want to think about it like this, the sum of the areas of all of these rectangles. Okay? So at any given point, the height of our, say we want to abate emissions by 35, okay? At 35, the cost of reducing emissions is about 50 euros per ton, right? And we would call that the marginal cost, the cost at the margin. But the total cost is the sum of all of the rectangles up to there, okay? Which we could, if we stylize this to a continuous function or curve, we would think of that as the area under the curve, or finally get back to your keyword here, we would, if you're mathematically minded, we would integrate. If you're not mathematically minded, don't worry about it, just think about the sum of the rectangles. Okay, so this is important because the idea of marginal amounts is really important in economics. So it's important you understand what a marginal abatement cost means. It means the cost of reducing the next ton of CO2. And that is distinct from, but related to, the idea of the total abatement cost, which is the sum of all of those marginal costs that you've paid up to that point, yeah? Which you get by the area under the curve. Okay, good. So the fourth question is a harder question, and in a way it's reaching forward to what we're going to be talking about in a couple of weeks, so you wouldn't necessarily expect very fluent answers on this yet, but maybe we'll get them, so I'll ask it. So the question was, how would we use a marginal abatement cost curve to inform setting a carbon tax?
Take the margin, like you would think about how much you want to abate and then see how much the marginal price is inside the marginal price.
Yeah, exactly. So in many political contexts, we might have set a target for the a reduction in emissions in quantity terms. Okay, so we might have set a target like minus 55% emissions by 2030. As in, say, the EU. And that will easily translate minus 55% into a physical quantity of emissions. It might be, let's just say it's 35 gigatons of CO2e. That would be if we had that target at a global level. Right? If we wanted to figure out, if we had to set a carbon tax that everybody had to pay, and to the best of our knowledge, it would deliver 35 gigatons of abatement, we would need to set the tax at the marginal cost at 35 gigatons, right? Because otherwise, if it were lower than that, we wouldn't get enough. Higher than that, we would get too much, yeah? But that is how we would use the MAC curve to inform setting a carbon tax. Yeah.
Does the existence of the negative abatement cost on here make that slightly questionable? In that presumably the people with the negative abatement costs already have an incentive to do so.
Yeah.
So presumably applying the tax might increase their incentive, but presumably there's other factors that are stopping them already.
Yeah. So there are two things going on here. So one is that in general, you always want to set the tax at the margin, and that inframarginal units would not need that amount of incentive to do it. But you have to set a single tax rate to incentivize everyone, so you would set it at the margin. The second issue you're raising is about whether this stuff needs incentivization in the first place, given that it's... but I don't want to say anything more about that for at least a few minutes, okay? We'll come back to it. But the fact that this curve goes under the x-axis does not really change the basic economic theory of this. You would still want to set the carbon tax at the marginal abatement cost. Right? It's say counterfactually, say this just trailed down to zero.
Yeah.
It does not affect that prescription.
So you said that we start from a goal that we have of reducing CO2 by 55% or whatever. Would it be the same to take the marginal damage curve?
Yeah, that's a good point. So we conceived of this as a cost effectiveness problem to start with. So we said that there's a quantity emissions target, and we would like to figure out what tax rate we need to set to achieve it, and we would set it according to the marginal abatement cost curve. If we move to a cost-benefit logic, then we would be wanting to take this marginal abatement cost curve and look at where it crosses the marginal damage or marginal benefit curve. And we'll think about that a bit more in a couple of weeks' time. Okay. The related question is, say I don't want to set a carbon tax, say I would like to use an emissions trading system instead. How would the marginal abatement cost curve be useful in that setting? Because it's different, isn't it? Yes?
if you set a cap on a specific commodity, you can use the curve to kind of figure out what the price would be.
Exactly. That's exactly right. So if I'm in the world of emissions trading, again, talk about this a lot in 2 weeks' time if this seems confusing at the moment, don't worry. If we're in the world of emissions trading, we don't need to set a price, right? We set a quantity, and that more or less follows straightforwardly from whatever emissions target we have. But then the MAC curve will give us an estimate of what permit price we would expect. Okay, so it will help us understand the likely economic consequences of the cap that we've got, and it will also help us look at prices in the permit market and understand things like, is the market functioning well? Might we worry about the exercise of market power in the permit market? Do we think that there's a problem with liquidity? Those kind of questions we would think about by comparing real permit prices with what we expected. Of course, the answer to that could be the model is wrong. There's no obvious, there's no unambiguous answer to that, but the information would be useful.
Could we also use that information to set like price caps or floors, or would we not want to do that because the model could be wrong and?
We would definitely want to think about price caps and floors again, and we'll talk about that in a couple of weeks' time. So I don't really want to get into that. Yes, I think that this kind of information would be relevant to that. Yes, because when you put price caps and floors in, you tolerate a level of quantity variation, and I think that this is helpful in understanding how much quantity variation you would expect. Okay, one last question then.
Yeah, I'm very curious about how we can estimate actually the marginal abatement cost curve. Do we use a long data panel and we run regressions, or what are, in the practice, what people does? Yeah.
You could do that, but really this is not as statistically sophisticated as that. This involves sending out lots of McKinsey analysts to collect information about the costs of different technologies. Okay, it's not generated from some kind of unified statistical or structural model. It's more of a desk-based research exercise. But we could certainly think about doing something econometric, which would lead to an estimate of this. Okay, now, that was really preamble. I'm sort of, I hope that we're all on the same page about what we're looking at here. And now, what I want you to do is I want to see whether you can distill some stylized facts about the economics of mitigation just from looking at this. Okay? This is going to be a little bit of pairing and sharing again for 5-10 minutes. I want you to look at this, and I want you to think, are there two or three key facts about the economics of climate mitigation that you're seeing here? And now my key steer for you here is ignore the detail. So I want you to look at this as if it's a Monet, okay? In the sense that it's better from far away than it is from close up. That joke is not mine, that's from Clueless, which was a movie. They used to talk about guys, about whether they were Monet or not. Let's not get into that. Okay, so, you get the point, right? Don't stare at these and think about, I don't know about this, I don't agree with the low penetration wind estimate, never mind, okay? Just look at the overall shape of this and characteristics of this, and see whether you can see some of the stylized facts of climate mitigation. So I'm going to give you about 7 or 8 minutes to do this. I'll give you a warning. And have a discussion, see if you can come to sort of 2 or 3 stylized facts about this.
then eventually
I think that unstylized pipe, it's easy at the beginning and it's very hard at the end.
more expensive.
That's the thing. I don't know. It's like Thursday, but yeah. But there's like a very steep But you can start one sided by trying to cover the side. Yeah, but I feel like putting money into savings are going to make the team like comparing to switching to LEDs. So the lab happens to make that decision.
And I don't know if these present value comps not taking into account is there that uniform carbon?
There's basically already without creating any cost. Better for you. That they will also not that expensive.
This one I was like, that one I don't
That's made it as well. Yeah, exactly.
Yeah, exactly. I think the point is because it's expensive, that's the unique level.
Yeah, so if you put a straight line across there,
The last thing to theorize might be too expensive.
Another thing is that it's a lot with energy. Are about you've got really energy agriculture and then heavy solar power. Yeah.
That's the thing that I feel like like I always need something like
Like stylized back. I was super simple. I said, all right, 10 gigatons, about a third.
And I was thinking, but like I know, I need to like bring it down.
10.
What?
You get 100 now.
Oh yeah, that kind of relates to
One minute.
It's like this. Risk. Yeah. Yeah. Mastering things.
But firstly, if you were signing the sign-up sheet over there and you happened to take a pen with you, could you please bring it back at the next break? Okay, so we are looking at this and we are trying to get 2 to 3 stylized facts out of this. So what did you come up with? What strikes you about this? Yes.
After the emissions are basically just a very good investment because there are negative costs.
Yes.
So
that is the first thing that I hope that everybody noticed. So we have this, according to McKinsey, this big tranche of emissions, about 10 gigatons, which apparently comes at negative cost. Now let's just stop for a minute. What does it mean to say they come at a negative cost?
It means that there's like a return on investment and include those investments.
Yeah, so irrespective of the climate benefit, these kinds of options should produce a positive return on investment. But how would that ever be the case?
We have already a lot of options. The action is more important to implement that.
So, I mean, we do have a lot of options, but that doesn't mean that they would be negative cost options, right? That's got to be something else about these options which makes them make lots of hands. Yes.
Like at the lighting example, LEDs are more efficient, so you would use less energy to light whatever building you swapped the lights out in.
Exactly. So that's a great example. Does beg the question though, how are these rectangles actually calculated? Does anyone know how the different costs at different points in the lifetime of these technologies are actually accounted for?
I was going to build on that negative cost. I guess it's almost indicative of some kind of barriers or information frictions, or just the kind of underlying techno-economic modeling being based on these like static engineering estimates, maybe not being accurate in terms of the practical implementation of some of these.
Yeah, so we are going to talk about this at length in week 8. Suffice it to say for now that the extent of this is controversial. Theories on it vary from it doesn't really exist, this is misestimated, through to no, it really exists. The reason why it exists are market failures and frictions which prevent rational actors from making investments with a return. But before we get into that, just sort of as a point of comprehension, does anyone happen to know how you would sort of actually calculate? I mean, how do you deal with the idea of a lifetime of a technology in one of these rectangles? Does anyone know? Yes.
So I think for the LED example, you would look at the investment cost of investing in new LEDs, and then the lifetime of that LED, and then how much at like average electricity prices they would reduce consumption.
Yeah, exactly. Very good. So, you know, one of the challenges of putting together a Mach curve is the fact that you've got different technologies which have different lifetimes, and also different cost profiles over their lifetime. And you've also got to implicitly compare them with a baseline technology that you assume would otherwise be used. So the light bulbs example is a great one. So, bearing in mind that we were working here in the early 2010s, so our baseline might be an old-fashioned incandescent light bulb, cheap to purchase, but uses a lot of energy and needs replaced a lot. And we're going to compare that with something like an LED, which is more expensive to purchase, but then uses a lot less energy and lasts a lot longer. So we actually need to add up both the upfront investment costs and all the running costs over an equivalent period of time, appropriately discounted, okay, in order to put them on an equal footing. And then we do that, and we boil that, and then we kind of, that's all in the background of these calculations, okay? So the negative unit cost of an LED light bulb basically it takes into account the fact that it's more expensive to purchase, but then it costs less to use and it lasts longer. And when you're making that comparison with a traditional incandescent light bulb, you also need to take into account the fact that we discount per last, right? So we do need the reduced running costs to be quite a bit larger than the upfront investment cost in order for this to give us a return. So hopefully that's clear how we've handled the issue of lifetimes and cost profiles. Yes.
In that specific example, would you model electricity prices over the lifetime, or would you assume?
Well, because you're making, I think that because you're making a comparison with a baseline technology, that probably just cancels out, basically. Because
but not if the efficiency is much
lower. No, you're right. No, sorry, I take that back. You would need to make an assumption about that, yeah. Yes.
I have another question regarding the calculations, not the costs, but the abatement potential, especially with all of the electrification strategies that are mentioned, especially in the low-cost part. How does the abatement potential include changes in like how the electricity will be constituted? Is it green electricity or like electricity from coal?
Yeah.
Is that how is that included? Is it with assumptions or? Is
it's with assumptions. So you have to fix on a baseline assumption about the incumbent technology in order to count, because these maps are based on differences with respect to that.
So you would assume that the electricity mix remains the same, or?
No, you don't have to assume that. But what you are raising is an issue which I did want to explain, so I'll explain it now. So and this relates to the fact that a Mach curve is essentially a static concept, but the problem of climate mitigation is a dynamic problem. So how should we think about this? So just in terms of emissions pathways to start with, so emissions and time, we've obviously got this issue that emissions are going up and we want to be going on a downward path. And then you might notice that this McKinsey Mach curve is for the year 2030, okay? So that might be somewhere like here. And what we're basically doing is that we are looking at the difference between the pathways in the year 2030. So we're taking like a static time slice of this pathway problem, yeah? So what would happen if I looked at this in 2040, yeah? So two things would happen broadly. So the first thing is that the emissions gap would be larger, okay? So I would need to, let's call that delta E1 and delta E2. The emissions gap would be larger, so I'd want to be considering a larger range of emissions reductions. But the other thing that would be happening is that the costs would be changing, okay? Because, for example, solar PV would be getting cheaper, right? So the curve would also be shifting over time, yeah? And it would probably be shifting downwards, right? Because clean technologies get cheaper typically as a function of both time and cumulative use, okay? So that is a dynamic problem, and it's not easy to visualize with a Mach curve, but you can think of a Mach curve as being a snapshot of the economics at a particular point in time.
So the cost for solar PV here would be, as they assumed in 2013 that in 2030 solar PV would cost like 20 euros.
Yeah, so two things can be happening, but yes, exactly. So this is an estimate of what solar PV would cost per unit in 2030, right? As made by McKinsey in 2013. Probably lower than that, by the way. I don't have the exact number, but we've been positively surprised by the falling price of solar. Again, we'll talk about that in week 8. I'm really pleased that you're all about 2 weeks ahead of where you should be. So two things can be happening as we go forward in time. One is that the cost will fall, but the other is we may want to assume there's some use of solar in the baseline. Okay, that is a question of our baseline emissions scenario choice as well, right? That a good baseline would not have fixed technologies probably. We want to think about how, normally the way we would construct a baseline is we'd think about how would technology evolve in the absence of a carbon price. And it may be that there is some solar in that system. But circling back to the stylized facts, we've got the first one, yes, negative cost. And hopefully you understand what that means. These should be economical, irrespective of climate change. And then the fact that these supposedly exist is a bit of a paradox, because rational economic actors should have done this stuff anyway. Okay, so what else do you see?
We talked about the sectoral mix that kind of changes as you go left to right in terms of the different industry, like the hard to abate industry showing up on the right-hand side. And that's even more prevalent, I know we're not there yet, but on the UK version where you can see the 2030 goal and all of the hard to abate industries past that.
I mean, exactly. I mean, almost by definition, the hard to abate stuff should be over on this side, because actually we do think about hard to abate as being expensive. It wasn't one of the main things I wanted to highlight, but it is possible to broadly characterize the different kinds of technology at different places on the curve. So a lot of the negative cost stuff seems to be energy efficiency, that kind of stuff.
And then like the nature, the agriculture, like in the center.
Yeah, exactly. Some nature-based solutions as well, which are sort of predicated on cheap land. In the middle, we seem to have a lot of the kind of conventional sort of renewables, nuclear kind of stuff. And then way over on the right-hand side, we seem to have all of the carbon capture and storage stuff. and some of the heavy industry and hard to abate. So yes, I think you could broadly characterize it like that. What else? I'm looking for really two more things. Yeah.
There's a limit to consumer-based mitigation. So there's parts like up until more or less 10, average potential of 10 gigatons per year, and that is more like technologies related to households consumption.
Yeah, I think most of the residential and energy efficiency stuff is over this side. Yes, I agree with that. Yeah, it's not one of the things I was wanting to highlight, but I think that's a fair point, fair reading of the chart. Yes.
The width of the bars in the middle is not visible on the edges. So like maybe the super low cost or super like high cost actually doesn't have as much abatement. Or like it's interesting.
Let me just look one slide ahead. I'm not sure whether that is generalizable to other math curves, but it is getting me towards what I wanted to. Yeah, I wouldn't read too much into that. I think that's a feature of McKinsey's calculations. But let me use this as a segue to what I wanted to say. So, no individual rectangle appears to be particularly wide, does it? I mean, there are just a lot of them, right? And they're mostly, I mean, at most we're talking about for nuclear, and we're talking about 2 gigatons. So we already know that there are many options. We knew that from the stuff we did in the first hour, right? But we also know now that there is no magic solution here, right? The economics is telling us, and this is I think this is a robust feature of different organizations' map curves. There is no single technology which is economic enough at a large enough scale of deployment to make this into a single technology problem. So suddenly we're starting to get a bit of economic traction now on this portfolio problem. The map curve we're looking at here is telling us that, yeah, this really is a portfolio problem, right? There isn't, among all of those stabilization wedges you mentioned to me, there isn't really a single technology that is going to crack this. We're going to need to do lots of different things. Yeah? So sometimes in the climate policy, sort of climate media, kind of climate comms discussion, I'll hear the analogy being drawn between climate action and sending people to the moon. Right, so climate change is like a moonshot. That is only a good analogy insofar as both are hard. Otherwise, climate mitigation is nothing like sending someone to the moon, because that is a very singular technological problem that can be solved by building a very large and capable space agency and building, or private company, as in the case of Elon, and sending rockets up, right? This is a much bigger problem with a more diverse set of technologies that we need. And this will, the kind of policy instruments that are going to work for climate change are heavily informed by this feature, okay? So I really want to emphasize this. Appears to be no magic solution here. No individual option that is going to give us more than 2 or 3 gigatons of abatement in 2030.
Maybe like sort of 2 weeks too early, but that basically also the technologies, right? And you just mentioned the policy side of things. Can it be that like with policy that is actually more that there's like 1 or 2 silver bullets that then drive this? Like how do we think about this in policy context?
That is a really interesting question. You are right that the choice of instruments can itself affect the menu of technologies that are available, their costs, and their technical potential. I don't think it's going to change it enough to change this qualitative story, okay? And you also have the problem of so-called picking winners with that. But generally, that is a great point you make. So the menu of technologies that are available is not independent of how you implement policy, the policies you choose. And yes, you are 2 weeks ahead, or even 3. Okay. So, I mean, what about the overall cost level? This is the last thing I wanted to talk about. What do you think about that? Yeah.
So I guess if you're looking at like the total abatement potential of, let's say, 38 gigatons, you could say that the price would be about 58 euros based on the chart. And theoretically, if you're able to price this, like the tons of carbon at this amount, you could get rid of 38 gigatons. I guess that's what the chart.
That is literally what it's telling us. Yes, you. And is that expensive or cheap? Anybody know what the price of an allowance is in the EU ETS? 170 at the moment. Okay. So, and you know, in Europe, energy and industrial sectors are parts of the EU emissions trading system. Price of carbon in that system is currently, I think, about 70 euros. Of course, you've all got your laptops in front of you, so you can verify my statement and tell me if I'm wrong. That's the fun of being a professor in the modern era. Whatever it is, it's going to be higher than, I'm pretty sure it's higher than 60. And we're still alive here in Europe with the EU. I mean, okay, in the UK we have a UK ETS, price is kind of similar, right? It hasn't driven us into destitution, okay? So, you know, at 60 euros a ton of CO2 equivalent, you know, this would be a very manageable economic cost. You could sort of reason about that by thinking of the price of carbon in existing emissions trading systems or existing carbon tax levels. Again, we'll look at that in a couple of minutes' time. You can even think about that by sort of multiplying your own personal carbon footprint by 60 euros and working out what share of your income that would actually be if you had to pay for that. For a person on an average income, it would not be enormous.
But doesn't that sort of mean that this is kind of like not accurate, this curve? Because like, okay, we're 5 years out or 4 years out, but like there's still quite substantial emissions in the EU, and that would almost mean like, okay, like we could get the EU on a 1.5 degree path.
Well, of course, yes, a good question to raise. So, you know, does the fact, the question here is, I'll paraphrase it, is that, well, if the EU ETS price is higher than this, doesn't this tell us that McKinsey were too optimistic? Or at least that's one way of reading your comment. Of course, this is a global curve, right? And we would potentially expect the marginal cost to be higher in Europe, right? Because it is a more advanced, already more carbon and energy efficient place than almost anywhere else. So it doesn't necessarily contradict it. But I will show you an alternative MAC curve in just a minute from a different organization which is not as sanguine. But before I do that, I'll just park the thought that, you know, the McKinsey MAC curve implies it's overall cheap. So, just to tie up this segment, I asked you to look at this like a money, and from this I wanted you to get 3 things. Firstly, I wanted you to see this negative cost area and consider the fact that we might actually be able to reduce emissions substantially without incurring any costs. Secondly, and probably most importantly, I wanted you to look at the sheer number of these rectangles and the fact that they're all quite narrow and infer from that that there is no single technology which has both the technological capacity and the low costs to make this into like a single technology problem. I mean, for some specific countries, it can look a bit like that. So there is a MAC curve for Brazil, which just has a huge slug of avoided deforestation at very low cost, okay? But at the global level, there isn't. And lastly, I wanted you to look at the cost at the margin of doing, you know, nearly 40 gigatons of abatement, which is a lot. That would bridge the emissions gap, and it's only about 60 euros a ton. which compares favourably with the price of carbon in several existing carbon pricing initiatives. And since none of those initiatives appear to have bankrupted the countries that have implemented them, tells us something indirectly about the affordability of this. But I'll show you some much more direct evidence on that a bit later. Okay. And now, just before I give you break number 2, just to bring us back from, teaching a climate change course does not typically involve much positivity. This gives us some positivity, but let's just get back to being negative again, okay? So this is much more natural territory for me. So this is an alternative MAC curve. This is a Goldman Sachs MAC curve at 40 gigatons of abatement. The marginal cost here is about $400 US, and to get to sort of into the 45s, we're talking about more than $1,000 US a ton, and only about 1 to 2 gigatons of negative cost opportunities. So obviously, this is going to vary from model to model, organisation to organisation. The points I've tried to get across, except for the last one, are pretty much robust across them. Sorry, did you have a question?
Yeah, what is the reason for the difference, like the massive difference between
Analyst judgment. Quite simply. Assumptions.
Do you know what year was this one?
2020. Well, actually, this is a MAC curve for 2020, so that is one issue. So the McKinsey one was a MAC curve for 2030. So there's some technology learning built into the McKinsey one, which is not built into the Goldman one. But I don't think that well, first of all, that wouldn't affect the negative cost part. And I don't think that would explain all of the differences in the positive cost part.
So something like the Brazil one where there was that huge chunk of deforestation, would that include like the loss of income from?
Yeah, so the correct cost concept here would be opportunity cost. So sort of what would the land otherwise be used for? So it would typically be the value of the land in agriculture or mining or whatever the land would be used for once it cut down trees. So it's not just literally, it's not just the cost of burning the trees I'm talking about, it's the cost of the alternative land use. Okay, let's take second break, another 10 minutes, start again, 4:50. Okay? Don't forget to pay amnesty. Whoever stole the pen, I'm not looking. Just bring it back.
He's so funny.
Yeah, but I study abroad, so nothing related to it.
It actually was, man.
I just can't sit. I'm gonna find out. It was so nice out this afternoon. Took like a 2-hour walk to come in. No, he. I was
Amazing.
like, didn't really have that much signal. Wasn't really telling you what was going on.
That's awesome. What here in London or? Awesome.
I was just like walking while I was
like just on the asset management side or sustainable investment?
and he ended up being like, oh, I'm on time.
Slightly depressed,
Oh, it was so good. Well, it's the thing with classroom. I mean, I did skip lectures. That's why I'm
level in the. But it is.
Is that your Sunday?
Just, I mean, this last week.
Maybe.
I'll try it.
Giant. No. Come on, I didn't care. I don't deserve to say we're on.
You make this yourself.
Okay, five, it should be around 400.
We need to do about 35 at the moment.
That's
so yeah, it would be
perfectly
consistent.
wasted dense for a
Be
brownie.
higher. Or
Well, it's a.
Oh, you're magic.
I'll just start bringing brownies. Why didn't we bring more? Actually,
So that's one of the best brownies I've ever had in my house.
This doesn't make you happy.
Cladding on the outside and on the inside.
They are quite expensive, but it's definitely.
Yeah, he says hello back.
that's
Six washers. Oh yeah.
It has that like
they're free.
No, I need a whole can, but that's part of their like whole like.
So like
yeah, they would be golden.
but it like they like I could do that. I could make that to give if you were reading me, I'll just like go read
And when work was busy, I would just like.
Girl, why are you laughing?
So I think about the that's all like refrigerated, but it's not.
Don't do Seven Sisters without us. I beg you.
that what?
Don't do Seven Sisters without me.
Okay, so I might do the white sisters, but it's not right. We're talking about sisters, but it's not yours. It's only like an hour and it's like 25 pounds.
That's I don't even have to blame out on
Tuesday.
So like a frozen dessert.
I was like the wind.
That's right, if the weather's okay, like,
That's what I was going down.
I was yesterday, like,
I was afraid that
yeah. So I don't know, like, I know, she's also,
You're ahead of you.
but you're more than close to like no, what I'm saying is I heard it's good. That's why
Here and
That is what I have. So like you guys are
How do you find it?
I've heard that it's like, if you don't think about it in that way and you just go into it with like, it's not gonna be a great movie, but it's gonna be a fun movie. I've heard it's like fun to like to yeah, no, exactly. Like you're not gonna get the deep story, but like you're gonna get a already involved.
And that's enough for
And that's enough for me.
Paul to his quiz.
We soon. I'm so oh my god, we should do that. Go after. That's a great idea. I freaking love it. I've been done with it like. Should we go tomorrow? Should we go to a public school? Sure.
Anything about
People finish Star Wars.
I've got the general knowledge.
Difference we can buy. You can bring brownies. I'm so hit or miss with what I know. I'm pretty good at geography, but it hasn't.
Almost everything. What I'm going to do in the last half an hour, 40 minutes or so, is just tie everything together and look at integrated models which simulate a low carbon transition and look at the results of those models which inform us about what a low cost, low carbon transition would look like. Okay? So a map curve itself is a component of these models. But these models that are used to produce low carbon transition scenarios, they are they take into account a wider range of factors, such as the evolution of baseline emissions and energy demands, the dynamics of technology costs, and so on. They are sometimes referred to as integrated assessment models. That is valid. It is a different branch of integrated assessment models to the ones we were talking about last week. These are the models that are built primarily to think about mitigation costs rather than climate damages. You don't need a damage function in these models to think about the low carbon transition because you can just impose a cumulative carbon budget as a constraint on the model and then get it to choose technologies and pathways that stay within the budget. So essentially you're solving a cost minimization problem, right? So min abatement costs to meet budget constraints. Okay? Now, what am I showing you here? What is the reason for this nonsense? Well, I just wanted to point out to you that just as IPCC Working Group 1 curates the climate models, and Dave Stainforth will have talk to you about that. So IPCC Working Group 3 curates these integrated assessment models or energy system models. Okay, so the different modeling teams, and there are of the order of 20 to 30 of them worldwide, run their models often with similar or identical socioeconomic scenarios and then produce comparable cost estimates. Okay, IPCC sort of helps coordinate and curate that operation, and in its assessment reports it gathers together all these scenarios. So for the 6th assessment report, 2,266 different scenarios, puts them through some vetting, gets rid of scenarios that don't even describe historical trends well, and then once the vetting has been completed, combines the emissions scenarios with simple climate models and gets that allows IPCC to basically put the scenarios into different buckets, categories according to end of century temperature, ranging from C1, which is 1.5 degrees with no or limited overshoot. That's what we normally think of as being true 1.5 degree scenarios, all the way through to C8, where the scenarios exceed 4 degrees of warming. Now, these scenario categories don't exactly have the sexiest names, but I'm telling you this because it's going to be important in interpreting the results in the coming slides. Okay? So IPCC is coordinating this, is collecting all the scenarios, putting them into buckets according to the temperature that the scenario reaches at the end of the century. Okay? The second half of the slide, I suggest we don't really need to worry about this. You can also take the scenarios and put them into different categories, not so much according to the temperature they reach, but rather according to the types of technology portfolio they use. And IPCC calls these illustrative pathways, or IPs. But we're not going to make much use of that today. Okay, so this is the thing that you need to bear in mind. And now what we're going to do is we're going to look at the results of the scenarios, and it's going to be one great big graph interpretation exercise for you, okay? We're going to show you loads of results. They're all going to have a very consistent format, okay? So let me just, so we're going to look at different types of results, starting with what happens to energy, going through electricity and hydrogen, investment, buildings, transport industry, and so on. For each one of these, you're going to see charts like this. What have we got here? So first of all, we've got 3 time slices, 2030, 2050, 2100. Okay, that should be fairly straightforward, right? What's on the y-axis is going to depend on what we're looking at, okay? Here we're looking at energy supply, and so the units are going to be appropriate to that, exajoules per year, so flow of energy, but it's going to change from one chart to another. For each time slice, you can see a series of box and whiskers plots. Do you know what a box and whisker plot is? Yeah. It's a way of characterizing the uncertainty. So basically, the underlying models are going to give you like a range of observations like that, something like that. And rather than plotting them all, you want to summarize it somehow. So first of all, we would locate the median, and for that we draw a horizontal line. Then we locate the interquartile range, okay, which we put in a box. And then we characterize the outliers by drawing whiskers, either to the 5th and 95th percentiles, the 1st and 99th, or just the ends of the range. So basically that's how you should read a box and whisker plot, right? So median, interquartile range, and extremes, yeah? And for each of these box and whiskers plots is the results for one of these temperature categories, okay? So as we, in all of these charts, as we go from left to right, we compare a very high warming scenario with a very low warming scenario. Okay? So, armed with this information, I want you to take a look at this chart and figure out what it's telling us about the evolution of energy supply over the century in low carbon scenarios. So 2 to 3 minutes with people around about you, see what you're seeing. Okay?
Scenario energy usage.
Since energy goes down,
Another one you go into after a certain and then if you look at high red,
across the charts, even aside from obviously layered growth.
That's true.
Energy needs to be more when exposing it.
What is it?
Even on the most negative scenarios.
Energy? Okay, yeah.
Yep. Roads very good.
Both 1.5 but can return again below 1%. The first one is that we never threshold. The second one is that we will go and overshoot, let's say, 20 years. Just never go above one. You always go like this. Yeah.
We're never gonna need
Yeah, they're like crazy.
like a nice.
The lower temperature scenario. Yeah, lower scenarios.
Before I think because in the high consumption energy consumption going up so much, renewable is not going down. Both.
It takes a bit of time to get used to these charts, I guess. But okay, so starting with total primary energy, so that's energy supplied from all sources. So what are we seeing here?
In 2100, it's remarkably flat across the. As long as you're below about 3 degrees of warming, they will have a similar primary energy demand. Whereas, once you go for trying to limit to 4 or going out above that, it's much higher energy demand. But actually, it's relatively agnostic to your warming level.
Yeah, and I would need to think about why exactly that is. Yeah. The important things I wanted to get across are, firstly, as you, certainly in 2030 and 2050, as you would expect, we see energy, primary energy, going down as we go to progressively lower temperature scenarios. Okay, so we're using less energy the more ambitious our climate targets are. But also, I wanted you to see that even in the most ambitious C1 scenarios, primary energy is still going up, right? So, reaching the most ambitious climate goals does not involve the world using less energy than it does today. Because population is still growing, we want economies to grow, energy demand is going to move to some extent in line with that, and these low carbon scenarios are able to do that, okay? But we're not using as much energy in a C1 scenario as we are in a C8 scenario, and that is the effect of energy conservation and energy efficiency. Yeah, the flatness I need to think about a bit harder why that's happening.
We thought about the flatness. We thought maybe it could be sort of difference between primary and secondary energy. So when you have sort of more sort of clean or like more electrified, those tend to be more efficient, and then therefore we thought maybe therefore it's pretty flat.
It's just heat also.
Yeah.
It could be, yeah, it could be. So you lose more energy in the with fossil energy, you lose more energy in the process of converting it into electricity and distributing it than you do with renewables. That is a possible explanation for that. But, okay, so that's what's happening to primary energy. What's happening to energy from fossil sources? That's pretty straightforward. It's going down, right? So low carbon scenarios involve using less fossil energy. That's blindingly obvious. What is slightly more specific is that low carbon scenarios basically leave you with zero coal without CCS by mid-century. Right? So that is a fairly robust feature of not just C1 scenarios, but also C2 scenarios and almost C3 scenarios. So coal is basically pretty much gone by 2050, but oil and gas are not gone. There's still, because fossil energy overall still amounts to something like 200 to 300 exajoules per year. Okay? That's not inconsiderable. What's happening to renewables? They're going up, right? So the opposite slope. So lower temperature scenarios use more renewables. Actually, one thing that I notice here, which reminds me to make a point, is that you see the compare the box and whiskers plots for C1 and C2 here, and it doesn't seem to make sense. They don't seem to be ordered intuitively. That is partly because there are not consistent samples of models, right? So these are so-called ensembles of opportunities. In other words, whichever scenarios were available, could be a bit of that going on here, adding noise. Yeah.
So are these groups mutually exclusive? So if you are in C1, you can't be in C2. So for example, like when they're looking at like limiting 1 to 2 degrees with a greater than 6-7% or greater than 50% chance.
I think they are mutually
You can't have
exclusive,
one
yes.
model that's in both.
I think it's defined in terms of 2100 temperature, and therefore each scenario is put into one and only one category. Okay, last thing, biomass, in other words, biofuels, also going up as the temperature target goes down. So in other words, low carbon scenarios using more biofuels. So that's primary energy. Next one, I'm just going to walk you through before I get you to do a bit more pairing and sharing. So this is specifically focusing on electricity and hydrogen. So energy from electricity is going up. Okay. That in itself is not overly surprising because energy use as a whole is going up. But it sort of follows from looking at what's happening to total primary energy, right, downward sloping across the categories, and comparing it with electricity fairly flat across the categories. What you can see here is electrification. So an increasing share of energy provided by electricity. And this is really, it's a sufficiently important point on the right on the board, because it's a common feature of, and perhaps not as obvious as the reduction in fossil, is that low carbon scenarios involve more use of electricity as a share of all energy, so electrification. And the share of low carbon electricity is close to 100% in 2050. Okay? So we are doing almost no generation of electricity from burning coal or gas without CCS. The amount of CCS that's being used is going to vary depending on the model and the scenario. Some of these models are going to have no CCS, which means that there are going to be no coal and gas plants, or very few. Some of them are going to be more optimistic about CCS, and then you can have more such plants. Last one is hydrogen. That's also increasing across the scenarios, but hydrogen is not a massive part of the energy mix in these models. It's typically being used for things like steel, aviation perhaps, shipping. It's not being used really for things like residential energy or some of the uses that people have suggested hydrogen could be useful for. It's been more for where you need a really energy-dense energy carrier. Okay. So, next one that I want you to pause and look at is energy investment. Okay, so the units here are money units, billions of US dollars. This is average yearly investments to 2050 across different kinds of energy technology. Take a look at this for 2 to 3 minutes and see what you're seeing here.
What's
T&D is transmission and distribution. Like power lines, basically. It might also be gas pipelines. I would just think of this as power lines.
That means they would be more expensive than the other ones that I can
Stand out.
Yeah, but more money to
Even in the
the other.
It's interesting because extraction is
So average yearly investment.
Like if you compare his
I don't, we're not comparing it to the baseline. I don't know what we are spending.
Yeah, I would say
If that is the constraint to where is it?
Solar.
We added all the C1
Which doesn't.
With solar.
That's a question. You're agreeing on the question.
Okay, yeah, so it's like plants, like. Yeah, and like all of the transmission, like all of the lines need to be connected.
Dude, I have like food. All my stuff like 1 minute. Just don't I don't use my bed. I don't take those things. Now I know that I just
Storage because in the low emission scenario there is more renewable.
Okay, let's bring it back together again. Okay, so I had a good question. I'll just clarify one thing for you. So extraction investment is upstream fossil fuel investment in like oil and gas wells, and fossil investment is like power plants, coal, oil, gas power plants. So that's how that. But in general, what are you seeing here in this chart? That's, yes.
It really stood out to us that storage is kind of an inverted outcome. So like scenarios.
Yeah, that's true.
There's like no.
No, there are only 4 scenarios in here. So I'm wondering how seriously whether this is a real economic phenomenon or whether this is just a sort of an artifact of there only being one model producing estimates of what happens in the C8 scenario with storage. But you're right. There's a weird pattern to that. I would probably prefer to just interpret the left-hand side of it.
But then the other one is 38, the scenario still goes up. So
yeah, no, it's true. With a very large confidence interval. But yeah, there could be something there. Yeah. I couldn't tell you what that is. Yeah.
In general, the more ambitious we are, the more expensive is the transition capital.
Yeah, so I think, okay, so first basic fact, which I think you've all got, is the fact that we're investing less in fossil fuels, both upstream and midstream and downstream, okay? And conversely, we are investing more in hydro, particularly in renewables and in transmission and distribution. Okay, so we're shifting capital from the fossil sector to the clean sector, and it looks like we may be investing more overall, right? If we took the effort to actually add these up across the different investment flows, right? And I think that's consistent with most macro models, which suggest that we do need actually a burst of investment in order to decarbonize. Okay?
One category that is often overlooked, but that is one of the largest in here, is that transmission and distribution.
Yeah, absolutely. So one of the things I was hoping would strike you is just how much we need to invest in transmission and distribution. It's already quite high in any scenario, right? And that reflects a lot of the build out of and the build out of electricity grids in middle income countries in particular. But you know, as you'll know, we need to do a lot more of that in low carbon electricity grids because we need to connect our renewables with the centres of demand, and that involves building lots of power lines.
Just for the sake of argument, we actually also thought about like the total length of all. And our takeaway was actually, okay, we may need to invest a bit more, but it may not be as much as we expect because like those lines almost equal out if you look at the extraction part on the right-hand side.
Yeah, it's not enormous. I mean, I don't think we're in a C8 scenario as the baseline, so I probably wouldn't take that as my point of reference. But even so, I think that you're right that the net effect on investment is going to be how the balance between investing less in the fossil sector and investing more in the clean sector. I think the net effect is going to be a little bit more investment on aggregate, but not an enormous amount more. But really, yes, these are the key points. I think you've got them. The redistribution of capital from the fossil sector to the clean sectors, and the great importance of transmission and distribution investment. Okay. Thinking about time, I mean, basically, just to so you know, everything is summarized at the end of the slide deck. Okay, so we can just skip a few slides and you can review it at your leisure. What I'm probably going to largely jump over is I'm going to show you. I've got the charts for buildings, transport, and industry. But I'll perhaps only just use in the building slide, I'll just drive home this point about electrification, right? The share of final energy provided by electricity. I'll perhaps also show you that in all scenarios, energy intensity goes down, so that kind of speaks to these negative cost options. It says that energy efficiency is a good thing to do in all scenarios, right? Almost irrespective of the climate goal. Okay, so that's also coming out quite strongly there. A bit of hydrogen in transportation, you can see that there, but huge error bars. Right, so a lot of disagreement in the models, and that actually propagates in transport through electricity and biofuels. So basically, the model's really not in agreement on what the fuels are going to be. Yeah.
So on the previous slide, it showed that geothermal was heavily de-emphasized, and then you bring up hydrogen there. And I was wondering, what's the reasoning behind that? I mean, it seems to some degree, even in the paper, like the writers are choosing winners and losers. Like, this is how the model's constructed. These technologies are going to get us there.
Well, so yeah. So the models.
What was the reason behind that?
Well, geothermal is very much limited by technical feasibility, and in large parts of the world, it just isn't. You just can't do it. Hydrogen is more illustrative of the point that, you know, as I said, all of these models are solving a cost minimization problem, right? So they're trying to they're optimizing the energy system to deliver a particular temperature goal. And therefore, the dispersion reflects differences in assumptions about technical potential and cost. Quite simple. And for something like hydrogen, which is barely commercially viable, except in its traditional fossil form. The uncertainties can be large. Transport industry is a kind of similar picture. So let's stop and look at land use for a minute. So take a couple of minutes to look at this slide, okay, 'cause it's quite interesting. So stepping to some extent, partly out of the energy system, but partly in it. But let's have a look at the land use sector. 2 minutes just. Go on.
Already just there is a lot of the bloom you increasing energy crops is forcing to reduce non-energy crop and pasture. Whatever those days continue to reduce the non-energy crops.
Yeah, I would say that.
I think it's for cows. Yeah, I mean,
It's just like the land, like that's the pH have like net negative.
Say that the less for soil. Yeah, but there is energy crops are getting
I assume it's because we're making
That's how a lot of that is.
Yeah, like
the carbon.
Yes, it's not as a proportion. The pasture decrease is meant to
If you do like carrots,
using like portion of land.
pasture land.
I don't know what the model is. I think it can either be more productive, maybe that, less.
Oh, okay, sorry. We're wind turbines. How do they produce
Bring it back together.
That's why it's
Okay, what are we seeing here? So, what does the forests chart show us? What is the forest chart showing us?
A lot of reforestation.
Yeah. So forest land is going up by about, median estimate, that looks like about 350 million hectares more forest in 2050. And earlier we looked at that, and reforestation and afforestation, is a stabilization wedge. Okay, I don't really have enough. I need to manage the time a bit more carefully. What's happening to pasture land and why? Yeah, it's you get your chance.
It's decreasing as time goes on across more or less every single scenario.
Yeah, and why might that be happening?
Either we discussed differences in diets, so less meat, or technological advancements as macro meat.
Yeah, so it's probably going to be primarily the former, and it's not necessarily going to be a sort of values-based choices, and this can happen too, but this could very probably just the fact that in C1 scenarios, beef and lamb become very expensive, right? Because they're priced at their they effectively become very expensive, and when the price of steaks becomes very expensive, people substitute away from that and start eating other things, right? And that is going on a lot in the models, right? In terms of crops. So we've got non-energy crops going down across the scenarios and energy crops going up across the scenarios. Well, so that's basically telling you that there is some reallocation of cropland from food crops to energy crops. How large is this? I put it into context, okay? So in 2020, global cropland was, get another pen, a red one, 1.6 billion hectares, okay? So 1,600 million hectares of cropland. So the these are not trivial changes, but this is you know, shifting things around a little bit at the margin here. Okay. Yeah, one question.
Isn't this somehow contradicting the pasture plot? Because take C1 for example, with like low like meat diet, but this would mean that we need like very high non-energy crop.
Well, we
very like it in C1.
I mean, I don't think of that as being contradictory. I mean, basically, we put a very tight carbon constraint on, and we start steering the global allocation of land towards uses which help reduce emissions. Reducing pasture land is a very effective way of doing that because it's quite an inefficient use of land, and the thing that's on the land is ruminants, which produce methane. So that's why that goes down. And we also, to some extent, want to use some cropland to produce energy crops rather than food crops. Okay. I don't really have much time left, so I'm going to just quickly walk you through the last two slides. So now we're looking at information on total economic costs. The first way we'll look at this is as we were looking at it earlier today in terms of carbon prices. Okay. So this box and whisker plot here gives you a number which is more or less directly comparable with the McKinsey number, okay, because it gives you the carbon price that would be required in 2030 in order for us to be on a 1.5 degrees pathway. This is a log scale, which makes it slightly a pain to interpret, but that is about 110, 112 US dollars per ton of CO2, $20-15. We'd obviously also want to multiply that by about 1.3. So we're probably talking about 140 US dollars a ton. So that is substantially larger than the McKinsey number, but not so large as to make this whole thing unaffordable. Okay, and you can see how much lower it is though as you relax the carbon constraint a little bit, right? So it's only sort of $80-90 for a 1.5 with high overshoot. And these numbers get very high as we go across the century, but the quantity of emissions that it's applied to becomes vanishingly small, right? So that's how you can sort of reconcile those two ideas. Not carbon prices here, rather percentage reduction in, I think this is actually percentage reduction in consumption, but we could basically think about it as a percentage reduction in GDP. So here is a number that's sort of comparable with the kind of things we were talking about in the last couple of weeks. So C1 scenarios in 2030, about a median estimate that to get on that scenario we'd be paying about 2% of GDP. So that's a 2% reduction in GDP relative to a scenario where we're not reducing emissions. Okay, so it's not trivial, but it's not a massive number. Remember, that's a levels difference between two scenarios. If you convert that to an effect on the growth rate, it would be extremely small. And that stays the uncertainty spreads out as we go across the century, but the numbers stay broadly in the range of 2 to 3%. So, that is it for today. All of the stuff we've done in the last hour is summarised in these 2 slides. You have your reading week next week, and I'll send you instructions about how to prepare for week 7, when for one time only we're going to have the fun of doing some problem sets.
Yeah, we should. But we need the weather to be better. But you can have loads of but I really want to do it.
Share it.
You'll make it. Well, I need to. Yeah.
Because you work here and you but plenty of people are leaving for
It's not the same. I think really that is just about the fact that the unit cost of a mitigation technology changes over time. So it's not about and by that I don't mean it's not about the cost changing over the lifetime of that technology. It's more about the lifetime cost of that technology changing over time as the technology improves or as wider factors affect it.